Okay, so for empirical formulas, all right, so basically what an empirical formula is, all right, it is your simplified formula, all right? And so what we're going to end up seeing is that we can think of it like almost like a family or a category of that we can put different covalent compound formulas into, all right? But we usually call it a simplified formula. So back when we were learning about naming, okay, for our ionic compounds, such as something like Mg2O2, right? If I had that on something, did you say that that was okay and that was correct? Mg2O2? This is when we crisscrossed charges, so no, like you guys would tell me that I have to simplify it, right? They would cancel each other out, so we would change this to be a 1 and a 1, right? So that was normal. So ionic things tend to be the empirical formula because that's just second nature. That's what you have to do for your ionic compounds. For covalent, that's not the case, and we got to see that. That's kind of why we were able to do that whole lab where we built the different molecules. You got to see the cool shapes, and then you knew that those shapes kind of went in line with the intermolecular forces, which gave them certain properties. So covalent compounds, you didn't do that reducing thing. So a common one that we are pretty familiar with, C6H12O6, right? We didn't look at that and simplify it to be a CH2O, right? Because what is this top one? What is C6H12O6? It is glucose, right? Is CH2O glucose? No, all right? Those are two totally different things. So we never simplified down. Now what we're going to see is this is technically like the family or the category, the empirical formula, the simplified ratio of glucose, okay? And that's going to be what we're basing our notes on, okay? There's a lot of application for this, such as in like forensic science and things like that, where we can get percentages of a sample that we're collecting from a crime scene, and you can then take those percentages and start to figure out which category, which family it's coming from, and then solve for a molecular formula or what the actual compound was, depending on properties and things like that, okay? There's a lot of application for it. We're just getting how we get to that number in the first place, all right? And then hopefully you guys get to do an activity that has a crime scene kind of investigation thing, all right? Hopefully. Just depends how things go. All right, so all of that description was this first part, all right? And so you can read that again if you need to, all right? But we're going to get into how to calculate your empirical formula. Oh, sorry, this part. If a molecular formula is given, you can always change it to empirical by just reducing the mole ratio, right? So just like what we did with glucose, we divided all of them by 2. We were able to come up with CH2O, okay? So easy enough. Don't overthink that one. All right. The calculating part, that's where you have multiple steps. So it's really important that you write down all these, or at the end, make sure you take a picture and write it down later kind of thing if you want to pay attention. I would just make sure you're following along with this part. I'm going to be writing a lot in this little space, so I'm going to keep mine very zoomed in. I just don't recommend writing big. If you are going to write big, then I would just probably go down to the bottom, and you can start kind of writing it in that bottom right corner. Okay, just my recommendation. All right, so how to calculate empirical formula given percent composition. So we have a sample, and we know that it's like 15% something and 30% something else and something, some blah, 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 blah. Right? So your step number 1, we are going to assume a 100 gram sample. We're going to assume a 100 gram sample. What that means is if I have 30% of something, it's 30 grams. If I have 15% of something, it's 15 grams, because we know percent is out of 100, so we're just going to assume that it's a 100-gram sample, and that helps us just go straight from percentage to these next steps. All right, so what that's going to look like on our end is that if we see a percent sign, we're just going to cross it out and change it literally to a gram. All right, you're just going to scribble it out and you're going to write grams. Okay, so if you want to lightly kind of color over that to show you that you're just changing it. All right, okay, once we got it in grams, our second step is we have to convert grams to moles. Convert grams to moles, which is kind of what we did just now in the warm-up, right? So when we convert grams to moles, remember, that looks like we're given something in grams. We're making that little T-chart looking thing. We're going to bring grams down to the right. We're going to have 1 mole up here, right? Our guaranteed 1. Who remembers what was the mass connection to a mole? Molar mass, yeah, which is your atomic mass. You get it from the periodic table. So I'm going to put mm down here, okay? So you're converting everything into moles. All right? So ultimately, if you want the shortcut right here, what this means is that you are dividing by molar mass, right? Ultimately, that's what we're doing. Since we're multiplying by 1 and we're dividing by molar mass, you're just dividing by molar mass. Okay, number 3. You're going to look at your numbers and divide by the smallest. Okay? You're going to look at your numbers. You're going to divide them all by the smallest. What this does for you is it creates a 1 mole, or creates 1 mole of something, meaning a 1 for a subscript. All right? Because remember, empirical formula and molecular formulas, we're looking to create the chemical formula with all those little subscripts. Okay? So this creates 1 mole for you. All right. Once you've divided everything by the smallest, you're going to round answers to a whole number. Okay? Because that is your subscripts. So put equals subscripts. Okay? Round answers to whole numbers, and that is going to make your subscripts for your chemical formula. Now, there is an exception. Okay? So if you have now ran out of room, feel free to turn your page sideways and write it right here. Okay? Right here or over here. That's fine too. I'm going to write it in right here. All right. So the exception is going to be if I have a number 0.5. So if I have a decimal that's ending in 0.5 after dividing all of them by the smallest, okay, 0.5 is not a number. It's terrible that we learn that, 5 and up, you round up, right? No, not always. When you get to this kind of stuff, like 0.5, that's not, you shouldn't feel comfortable rounding that up or rounding it down. It's right in the middle, and you can't say which direction it should go, right? So if we want to get to more of a definite thing, which is kind of like 0.7 and above or 0.2 and below kind of thing, then we want to try to create that whole number. What can we multiply 0.5 by to create a whole number? 2, okay? I keep holding up one finger. I'm like, 2. But yeah, it's 2, okay? So if you have something that ends in 0.5, and we're going to see that in our example number 2, okay, you're going to multiply by 2. And when I say you're going to multiply by 2, you got to multiply all of your subscripts. We don't have enough room to write that. If you have something that is a 0.3 or 0.6, what do you think we should round or multiply those guys by? How can I get 0.3 to be like 0.9 times 3? Okay, so both of those we're going to multiply by 3. And then you guys might see when we're doing our little activity on a later date that if you get 0.25, I've had people just make that a 0.3, but technically 0.25, what do you think you're going to multiply by? Think of how many quarters are in $1. 4. Okay, but we're not going to write that one down. Okay, so those are the steps, and I would say, honestly, this is like the most difficult things get because it's just a lot of tedious little itty-bitty steps, and it's important that you go in order and you follow them, okay? So if you get through empirical formula, you're in a good spot, I would say. You're going to be good for the rest of the year. All right, so find the empirical formula of a compound that contains 32% sodium, 22, da-da-da-da-da. So we see that we have 3 different elements. We're going to just follow these steps in order. So the first step, we're going to assume a 100-gram sample. That means that we're going to change all of our percent signs to be a gram sign. So I'm just going to scribble out each one of those percents just like that. And I changed them all. Now they're all in grams. 100-gram sample. Piece of cake. Step 1 done. Okay. Step 2, convert all of those grams now to be to be in moles. Sorry. So we're going to have for sodium, I have 32.38. So 32.38. I'm going to bring words down to the right. That was grams. Down to the right, and I'm going to have my molar mass. So I'm going to look at my periodic table to figure out what sodium is. Sodium should be 22.99. Yeah, 22.990. And that's connected to 1 mole, so that's how we're converting, right? So we're going to multiply across, divide by the bottom. So that gives me the answer 1.40. 1.408. I'm just going to do that, okay? Don't want to round yet. All right, so sulfur, I have 22.65. So for sulfur, I'm going to go ahead and write 22.65. Do the same exact thing. Molar mass, according to my periodic table, is 32.066. 1 mole. So that one's going to come out to be 0.706. And then finally for oxygen, I see that I'm going to run out of room, so I'm just going to kind of squeeze this down here at the bottom. For oxygen, I have 44.99. So I'm going to have 44.99, and I'm just going to use the simplified version, which is divide by the molar mass. So I'm going to say divided by 15.999. And I get 2.81. Okay? 812. All right. Step 2 is done. That's probably the longest one. All right, so now we're in step 3. We're going to look at our numbers. So you're looking at those 3 answers that we just got. We're going to divide them all by the smallest. So which is your smallest number here? Yep, the sulfur one, right? So I'm just going to circle that for our notes purposes. And I'm going to say, okay, that's my smallest. So I'm going to go ahead and say divide by 0.706, divide by 0.706, divide by 0.706. So when I plug those in, I got 1.99. This one I've got 1. I was about to type that in. And then 2.812 divided by 0.706 gives me 3.98. All right. Last step says round. Yes. You're good? Okay. Yeah. So last step is we're rounding our answers to whole numbers. So 1.99. What are we going to round that one to? A 2. 1 is just going to stay a 1. And 3.98 is about 4. So that's our answer. We're going to have Na, right? Answers are the subscripts. So we're going to have Na with a little 2. We're going to have S. We don't write 1, so I'm just going to leave it in S. And then I have O with a little 4. So anybody know what this compound's called? It is sodium sulfate. Good. All right. So this is an ionic compound, which means the empirical formula was the actual formula. All right. But that's running through all the steps. Got it? So I would say the biggest mistake that happens is people round at this step. So looking at this, they would have said, oh, don't I have to double this one or things like that. Don't round too early. You have to always divide by the smallest, and then you have those obvious ones. All right, so example 2. Just because this one actually has one of the examples of where you're going to end in a 0.5, right? So example 2, just running through it slightly faster. So analysis of this sample, okay, of a compound known to contain only phosphorus and oxygen indicates a phosphorus content of 4.433 grams. What is the empirical formula for this compound? So, yeah, we can just do this. All right. So a couple things that are different now. Did we get any percents? No, right? So if you don't have percents, don't worry about changing anything. Like you get to fast forward straight to step 2. Okay, so don't freak out if you don't have percents. If you really wanted to, you could figure them out, but don't do that. But you have two elements that this thing is going to be made up of. So we have phosphorus, which we know is 4.433. And converting that into moles, I know that I'm going to bring words down to the right. Phosphorus has a molar mass of 30.974. Again, from the periodic table, 1 mole above. So we're just dividing those. And you get the answer 0.143, right? So we have that in moles. All right, cool. Then we go to do oxygen, right? Well, do we actually have a number for oxygen yet? We could have it, right? But we have to figure that part out real fast. So we have a total sample. So we know that 10, so this is an extra step.